Hello, this is the video number 7 regarding the linear second order differential equation, and I'm going to talk today about part 2, which is related to the constant coefficient case. So this is our topic for today. Okay, let's go to the next. This is the title, and big as we said, this is the constant coefficient case. Let me use the laser pointer here so that this would be better for us. Okay, now let's go to the constant coefficient case and what is the meaning of it and why we are dealing with this case now. So we need to understand some points here before indulging into the main topic of the constant coefficient case. Up till to the last lecture, we already have outlined strategies for solving second order linear homogeneous and non-homogeneous differential equations. If you recall the last lecture or last video, you are going to find that we have already outlined some strategies and we have discussed them. And in both cases, whether for the linear homogeneous or non-homogeneous differential equations, we found that we must begin with two linearly independent solutions of a homogeneous equation. So our baseline is how to find a solution or two solutions for the homogeneous equation. Okay, the homogeneous equation or the associated homogeneous equation with the non-homogeneous equation. So we have to find firstly what two linearly independent solution of the homogeneous equation. So this is the baseline here. So now this can be a difficult problem actually. To find the solutions or two linearly independent solution can be a difficult problem. However, when the coefficients are constant, we can write the solutions fairly easy. Okay? How we can do this? So this is what we are going to explain. The point here, the word coefficients, this is the key word. Okay? What is the meaning of coefficients? We are going to explain it in the next slide. So let's consider the constant coefficient linear homogeneous equation that you can see here. Actually, this one, as you can see, it is y double prime plus a y prime plus b times y equal to 0. This is our constant coefficient linear homogeneous equation. Constant coefficient means that we have like constant coefficients here. As you can see, it is a and b. So this is a very unique shape for the differential equation, and it tells us what or how we are going to solve this equation, in which a and b are constants. They are numbers. So a and b, they are constants or numbers. A method suggests itself if we read the differential equation like a sentence. Actually, that we are going to look to this equation as if that we are writing or we are reading a sentence. What this sentence says to us, we want to say, or this sentence is like this, that we want a function y such that the second derivative, which is this one, plus a constant coefficient of the first derivative plus another number or coefficient times the function itself equal to 0. Okay, this is reading the equation as if it is a sentence. Okay, this behavior suggests an exponential function e to lambda x. Actually, whenever you look to this, you're going to find that this differential equation, if we want to satisfy it, we need something like this, that the second order or the second derivative of the equation plus a constant times the first derivative plus a constant times the function itself equals to 0. Actually, we have one function that is going to make it easier for us to solve this equation. This function is the exponential function. Why we have chosen this exponential function? The point is because derivatives of the exponential function here, which is e to lambda x, are constants or constant multiples of e to lambda x. Constant multiples of the function itself. Okay? So this is the main reason for us to use this exponential function and suggest it as a kind of solution for our differential equation. We therefore try to find lambda so that e to lambda x is a solution. So our main problem now is going to be narrowed down to lambda only, which is the power of the exponential function here. So substitute, let's play with this. Let's substitute e to lambda x into this equation. Okay? So we are going to have the second derivative of e to lambda x, which is going to give us lambda squared e to lambda x, because this is the second derivative of e to lambda x, right? So it is going to be lambda squared here, times the function itself, e to lambda x, plus we have here a times the first derivative of the exponential function, so it is going to be a times lambda times the function itself, which is e to lambda x, plus b times the function, which is e to lambda x, equals to 0. Then if you look to this equation, what we can do with this equation, let me use the pen here so that we can get the meaning. I'm going to write it here. I'm going to take e to lambda x as a common factor. So this is e to lambda x, as you can see here. And then I'm going to open a parenthesis. The first one is going to be here lambda squared plus a lambda, right, plus b equal to 0, right? This is what we're going to have here. So the point is, we took this e to lambda x as a common factor, and we put the remaining lambda and constant coefficients in or between the parentheses, as you can see here, and we equate it to 0. Now the question is, do you think that if we are having two terms multiplied by one another and the right hand side of them is going to be 0, this means that either this term is going to be 0 or this term is going to be 0, right? So looking deeper in this, you're going to find that e to lambda x, it's a non-zero term, right? E to lambda x, it's an exponential function. It's always positive, and it's never 0. It's never equals to 0. So the exponential factor here cancels out. It is cancelled. And we are left with the quadratic equation, this quadratic equation, which is a function of what? Quadratic equation, because it is lambda to raised to the power 2 plus a, which coefficient, this coefficient times lambda. Remember that this a comes from where? Exactly. It is the constant coefficient of the original differential equation. And then plus b, which is what? It is another constant coefficient in the equation or the differential equation. So now we are dealing with this, that e to lambda x times this equation equal to 0. Then we are going to equate this quadratic equation to 0, right? So we are going to put it like this. We're going to say that the solution for our differential equation is going to be obtained by an exponential function. This exponential function is e to lambda x, and after substituting in the main differential equation, we found that after rearrangement that the lambda that we have assumed going to be or going to shape our solution, and the coefficients of the original differential equation is going to be or equals to 0, as we can see here. Now we started to find that there is something that we need to do, that this quadratic equation, now it is easier, much easier for us to solve compared to the differential equation, right? So let's go here. This is a quadratic equation, and whenever we have quadratic equation, the solution of it is what? Exactly let's have a look here. This is our differential, this is our quadratic equation, lambda squared plus a times lambda plus b equal to 0. The above quadratic equation is characteristic equation of the following differential equation, which is the original differential equation. We say, or we put a title for this equation, we call it characteristic equation. So lambda and the coefficients are composing the characteristic equation of the original differential equation. Okay? This one we're going to find that it is easy to be solved, as we can going to explore right now shortly. Okay. So now let's focus on this equation, which is the characteristic equation. Lambda squared plus a lambda plus b equal to 0. The characteristic equation has roots. This is the roots, right? Do you remember the roots of the quadratic equation? Okay. It has two roots because it is raised to the power 2. So we're going to have here, this is always, the coefficient here is 1, and we have here a, and we have here b. So the two roots of this equation is going to be 1 over 2 between parentheses minus a plus or minus, from here we have two roots, the square root or the radical of a squared minus 4b. a squared minus 4b. Okay? So we are going to look to this equation or these two roots, okay, deeply. We have two signs here, which means that we are having two roots, and we have a term under the radical, which is, we call it a squared minus 4b. Okay? This term under the radical is going to give us the three main cases for the characteristic, for the roots, and also three different solutions for the characteristic equation. Okay? So now looking to this, leading to the following three cases. We have three different cases. Okay. The first one, the first case, which is case number 1, it is going to be, we call the roots in this case, real distinct roots. Real distinct roots. Why it is real? Because it is not imaginary. Distinct because they are not repeated. They are different. Okay? Roots because we are talking about a quadratic equation, so we have two roots here, as we said. Okay? So this occurs when the term under the radical, let's go back here, larger than 0. Let's go back. This term, a squared minus 4b, this term. If it's larger than 0, this means that the roots are distinct. The distinct roots are lambda 1 and lambda 2. Lambda 1 is going to be half times minus a plus the radical a squared minus 4b. And remember, this radical is going to be under the radical. They are going to be a number which is larger than 0. And lambda 2 is going to be half times minus a minus here, and instead plus here. The same term, which is the radical of a squared minus 4b. Close the parentheses. From here we can obtain lambda 1 and lambda 2, which are the characteristic or the roots of the characteristic equations. So we have e to lambda 1x and e to lambda 2x are linearly independent solutions. It's very important here. They are two linearly independent solutions. And in this case, the general solution of the equation, which is equation 2.3, let's go back to see where this is. This is the equation of 2.3, the main differential equation. We call it constant coefficient linear homogeneous equation. Okay, so this, in this case, the solution is going to be like this. Remember it well, because we are going to solve our equations based on this shape of the equation that we are going to put. Y, okay, is y equals to, this is the general solution, a constant, a number called C1 times e to lambda 1x. What is lambda 1? It is the first root here, this one. Okay. Times the exponential function raised to lambda 1 times x plus C2 times e raised to lambda 2 x. What is lambda 2? Exactly, it is the second root of the real distinct root. The second root of the real distinct root. Okay, so now this is the first type of solution that we're going to have if we have the shape, or we have the term under the radical to be larger than 0, as you can see. Well, this is very nice. I think that we are ready now to have an example. Okay, let's have an example from the differential equation. Okay, this is the example: y double prime minus y prime minus 6y equals to 0. We immediately read the characteristic equation. Okay, now we can read it from the main differential equation. Okay, how we can put it? This is the characteristic equation. How we did this? Remember that here, let's use the pen here. So here, this is a, which equals to -1, and this is b, which equals to -6, right? So this means that we have lambda squared, right? And here this is a lambda, and -6, which is the free term, and it equals to 0. If you are going to solve this with the differential, the law, you are going to find that we have two roots here, which is 3 and -2. 3 and -2. So this means, as having real distinct roots, okay, this is the case for us. If you are going to check the radical for this equation, you are going to find it larger than 0. And if you are going to get the coefficients a and b, it is very easy from the equation here. This is a, this is b. Then you are going to put it as the characteristic equation is going to be, as you can see here, which is lambda squared minus lambda minus 6 equal to 0. If you are going to solve this using the law, you are going to find that you have two distinct roots. The first one is 3, and the second one is -2. So as having real distinct roots, 3 and -2, the general solution is, as you can see here, y equals to c1 e to 3x, this is the first root, plus c2 times e to -2x. Okay, this is the general solution for us. Okay, so again, what I have done here, it is pretty easy. Just from the differential equation, as you can see here, I looked and found that I have the second derivative without any coefficients, which is coefficient 1 here. The first derivative with -1, and the function itself multiplied by a value, okay, or a number, equal to 0. Then if we go back to the main equations or the main derivations that we have said, this is, as we said here, this is our differential equation: y double prime plus a times y prime plus b times y. We have a here, we have b here. If you go here, so we are going to put our characteristic equation as lambda squared with coefficient of 1 plus a times lambda plus the free number, which is b, equal to 0. Okay, this is actually what we have done here. So -1, which is times minus lambda here, -6 here, which is times the function in the original differential equation, is going to be the free term in the characteristic equation. And then this is algebraic equation. It's polynomial. It is a second order, or we can say it is quadratic equation. Very easy to be solved. You can solve it easily and find the roots of lambda, right? It is going to be 3 and minus 1. Then the solution is, let's go back and see the solution. Our general solution is going to be y equal to a constant number C1 times E times lambda 1x plus another constant C2 times E to lambda 2x. So this is the general solution. Let's go here. Y equal to C1 E to 3x. This is the first root of lambda, 3 as we said, plus C2 times E to minus 2x. This is minus 2, which is the second root of this equation. Okay? Pretty easy and straightforward. I think that it's not difficult at all for anyone to solve the constant coefficient case for the differential equation in that shape. Okay. Now let's go to the second part, or the second case for the for our roots. If you remember, we said that if the term under the radical, which is a squared minus 4b, larger than 0, then we are going to have real distinct roots. But here we put equals. It is equal to 0. So the root of the characteristic equation is going to be repeated roots. We are going to have the same root. For this case, we are going to find that lambda equals to minus a over 2. Always. It's only one root. It is always one root. Okay. The general solution in this repeated roots case is, this is the solution directly. So the mathematicians already, they got this solution for us, so we can use it directly. It's an application for us. Y is going to equal to C1 times E to minus AX over 2 plus C2X times E to minus AX over 2. So they are going to be like pretty similar, pretty the same, except that we have the term X here. So they are going to be the term X here, but almost the two terms are identical. Okay, so this is the second case for us. Let's have an example that is going to solve, that we're going to solve, and we're going to find that it's easy really to solve this equation. Okay, so our equation is y double prime plus 8y prime plus 16y equal to 0, or is equal to 0. The characteristic equation in this case is going to be, looking here, this is a, which is plus 8 or positive 8, and this is b, which is positive 16, right? So without doing anything, I'm going to write the characteristic equation as lambda squared here plus a times lambda, which is 8, plus b, which is 16. So we are having this in the left-hand side, and the right-hand side we have 0. A very simple, straightforward quadratic equation with a single root. We can do it easily by the law, and you can get it by yourself. Train yourself on such kind of small jobs during the exams and so on, and during your assignments you need to solve it quickly. So we have the repeated roots here, which is lambda equal to minus 4. The general solution is y equal to C1, an arbitrary constant, times E raised to minus 4x plus C2 times x times E to minus 4x. So we have this equation. Okay? Okay. So this is the second case. Let's go now to the third case. Let's go to third case. Okay. In the third case, we call it the complex. We call it the complex case. The complex case. So the characteristic equation, in this case, has complex roots when a squared minus 4b less than 0. So the term under the radical is going to be less than 0. Less than 0. Because the characteristic equation has real coefficients, the roots appear as complex conjugates. So we are going to have a conjugate here, complex conjugate. Alpha plus iota beta, and alpha minus I or iota beta, in which alpha can be 0, but beta is non-zero. Okay, so remember that well, alpha can be 0, but beta is non-zero. Now the general solution is, we are going to take it directly. Actually, there is a derivation in the book, but you can go through the derivation, but you're not going to be asked in the exam regarding the derivation, okay? So you can apply the equation directly. Y equal to C1 raised to the first root, which is going to be alpha plus I beta x, and plus C2 e2 alpha minus I beta x. And we can take e2 raised to alpha x as a common factor, and then between the parentheses we're going to have C1 e2 I or iota beta x plus C2 e2 minus iota beta x. Okay, so this is how it works. But whenever you look to this equation, you're going to find complex numbers, which is iota here, which is something that we do not like in general. Okay, it's easier for us to get rid of these iota here. So we are going to work on this equation and try to change it, okay? And instead of using the imaginary numbers or complex numbers, we are going to use the trigonometry, okay? The sine and cosine, or the sinusoidal, okay? Equations or functions. Let's go here. So we can say that, because as I said, it's sometimes convenient to have solution that does not involve complex numbers, we can write the general solution with no complex numbers as follows. So actually also it has a derivation, but as I said, the derivation is omitted. No need to, you can study if you like to know the derivation, but again, at the exam you're not going to be asked about the derivation. Y of x equal to C1 e raised to alpha x times sinusoidal function, which is cosine beta x, plus C2 e2 lambda x times sine beta x. Okay, so this is the equation, this general solution, the general solution for the case of the complex number. Or we can say, or y of x equal to e to lambda x times C1 cosine beta x plus C2 sine beta x. This is going to be the same because just we have taken e to lambda x as a common factor. Here we took this as a common factor, so I think that it's not a big deal for us. Okay, this is the most common one that we usually use. Actually, C1 and C2, as we said, they are constant. They are arbitrary constants. Okay. Let's have an example and see how it can be solved here. The example is, solve this equation y double prime plus 2y prime plus 3y equals 0. The characteristic equation, without thinking too much, we have a here, which is 2, we have b, which is 3. So our characteristic equation is going to be lambda squared plus 2 lambda plus b, 3, equal to 0. With the complex conjugate, if you are going to find this, if you are going to get the law of this equation, I put it here only for clarity, but you need to do it by yourself from now on. So this is the characteristic equation. I put it here, equated to 0. And then I said that the roots of it is going to be lambda equals to minus 2 plus or minus the square root of 2 squared, which is this coefficient, minus 4 times 1 times 3. 1, this is 1 here, and 3, this is the b here, okay? Over 2 times 1. Then this would equal to minus 2 plus or minus 8, okay, over under the radical, and minus over 2. And then after making some rearrangement and cancelling and putting this minus 8 and putting the 4 underneath the radical, I mean this is coming from 2, then you're going to end up with minus 1 plus or minus I times the square root of 2, which is this one. Okay, so you can check it by yourself here. You can check it by yourself. So if you look to this one, this is going to be what? Exactly, this is alpha. So alpha is going to be minus 1 plus or minus iota times beta. So beta equal to, exactly, beta equal to the radical of 2, or the square root of 2. The general solution in this case is going to be y equal to c1 e to minus x, because we have alpha is minus 1, so it is going to be e to minus alpha x, which is minus x, cosine beta x, beta here is square root of 2, x is here, plus c2 e to minus alpha x, which is minus x, sine beta x. So this is the solution actually of the differential equation. This is the solution of the differential equation. Okay, so let's have another example, and then we're going to wrap up this part. Here we have solve this equation, which is y double prime plus 36y equals to 0. The characteristic equation is, reading from here, 36, it is going to be, exactly, it is going to be our b. So we have lambda squared plus 0 plus 36. Because where is a here? Exactly, a, it doesn't exist, because y prime doesn't exist. This means that a equal to 0. So our characteristic equation is going to be lambda squared plus 0 times lambda plus 36 equals 0. Okay. With the complex roots, if you solve it, and please solve it by yourself to find that the complex roots of this equation is going to be 0 plus or minus 6 iota. So alpha is going to be 0 and beta is going to be 6. So the general solution is y of x equals to c1, okay, times e to alpha x. So it is going to be 1 here. So here, this is, because this is the equation, let me use this one. So here it is c1, actually it's supposed to be e to alpha x, which means that e to 0 x means that we're talking about 1 here. Okay, similar case is going to be here. Okay, so this is the case for this equation, Okay, let's go to summarize what we have said up till now. So as you can see, we are now able to solve the constant coefficient homogeneous equation y double prime plus ay prime plus by equal to 0. We understand now why we call this constant coefficients, because we have the constant coefficients here, a and b. In all cases, here is a summary, okay? We can solve it in all cases. Here is the summary. Let lambda 1 and lambda 2 be the roots of the characteristic equation, which we can compose from this differential equation. It is going to be lambda squared plus a lambda plus b equal to 0. So if we have lambda 1 and lambda 2 to be two distinct roots, or maybe they are going to be the same root, or maybe they are going to be complex roots. So we have 3 cases, right? So let's explain and summarize our 3 cases here. We have case number 1, where that lambda 1 and lambda 2 are real distinct. And we have case number 2, which is lambda 1 equal to lambda 2. And case number 3, where that the roots are complex, alpha plus or minus iota beta. In the first case, where that lambda 1 and lambda 2 are real distinct roots, our general solution of the differential equation, the constant coefficient differential equation, is going to be C1 times e to lambda 1x plus C2 e raised to lambda 2x. This is the general solution. In the second case, if we have repeated roots, then our differential equation solution, or the general solution, is going to be y of x equals to C1 e to lambda 1x, similar to this case, plus C2 times x times e to lambda 1x, similar to this case, but we are increasing that there is x here. The function x, or the independent variable here, is added. And in the third case, if the roots are complex alpha plus and minus iota beta, then our general solution is going to be y of x equals to C1 e to alpha x times cosine beta x. So we get rid of the complex number by adding sinusoidal function cosine beta x plus C2 e to lambda x sine beta x. Okay, so this is the three cases that we are going to encounter. We have solved solved the different examples. So I'm going to recap what I have said here. So our main title is the constant coefficient case. It's a way for solving the differential equation. And we said that whenever that we are going to solve our homogeneous or non-homogeneous equation, we are going to go into the first step, which is finding two linearly independent solutions. Okay, so how we can find these two independent linear solutions? We found that if our differential equation looks like this equation, we found that we are going to assume a solution called e to lambda x, and we substituted here. And we found that by some mathematical logic, we found that there is some equation called the characteristic equation, which can be formed from the coefficients of the original differential equations and a lambda, which is one of the parameters of the assumed e to lambda x as a solution for this equation. Then we found that for the solution of our original differential equation, we need to solve this quadratic equation and the characteristic equation. We found that we have three cases actually for this. So we found that this is quadratic equation, and it can be solved with the law, as you can see here. And this law is going to be controlled by the term under the radical. So we have three cases. The first one is the real case, where that the roots are real distinct roots. So we're going to have lambda 1 and lambda 2, as you see here. And our general solution is going to be C1 e to lambda 1x plus C2 e to lambda 2x. And after that, we mentioned about the second case, where that repeated roots, our roots are going to be repeated, where that the radical, or the term under the radical, equal to 0. In this case, lambda equal to minus a over 2, and our general solution is going to be C1 e to minus ax over 2 plus C2 x e to minus ax over 2. Okay. And then the last case is going to be the complex roots, and we said that the complex roots is going to be solved by having, and we said that the complex roots where that the term under the radical is less than 0. In this case, the solution is going to be e to alpha x times c1 times cosine beta x plus c2 sine beta x. Okay, this is considered to be the summary of our coefficient case for today. And we have many examples, like 6 or 7 examples on the total topic. So we are going now to have the in-class assignment. So now you can stop, okay? You are going to, you can stop the video and look to the next in-class assignment and try to solve it, okay? Actually here, okay, just you can go through this. This is the problem that we have. So as I said, you need to stop the video here, look to this problem, which is the in-class assignment for you. You can do it only during the video while that you are doing the video, so or watching the video. Our equation is y double prime plus 6y prime minus 40y equal to 0. Okay, try to solve this by yourself, and then you are going to find the solution. The solution here, this is the model answer if you want it. So we are going to say that our characteristic equation can be drawn directly from the differential equation. Then we have 6 is A minus 40 is B. So we are going to have our characteristic equation lambda squared plus 6 lambda minus 40 equal to 0. This quadratic equation can be solved using the law to find the lambda. So after substitution, we can find that lambda is going to be two real distinct values. Lambda 1 equal to minus 10, lambda 2 equal to 4. And based on this, the general solution is going to be y equal to c1 e to minus 10x plus c2 e to 4x. This is the solution. This is the general solution. Okay, now let's go to another in-class assignment. You can stop the video here. Just try to solve it before looking to the answer. Solve it by yourself, okay? Solve it by yourself. Y double prime plus 3y prime plus 18y equal to 0. Then, in the same sense, we are going to put this is the differential equation. We are going to draw, where is the A and B? A is 3, B is 18. Our characteristic equation is lambda squared plus 3 lambda plus 18 equal to 0. And lambda is going to be, yes, this is the law. You can substitute in the law. And then you are going to end up that lambda is going to be complex number. Because simply the value under the radical here, it's seemingly to be what? Yes, less than 0. So we are going to have complex roots here, which is ending with minus 3 over 2 plus or minus I times this. From here we can say that alpha is minus 3 over 2, beta is going to be 3 radical 7 over 2. Then y is going to be the final general solution is going to be e2 minus 3 over 2x times c1 cosine beta x plus c2 times sine beta x. Okay, so this is in-class assignment for you. I hope that you can solve it without looking to the solution, okay? And then check the solution. Now let's go to the final part, which is the home assignment, Now the first home assignment is this. Solve this equation. And remember that it is going to be, yes, it is an initial value problem. So we have here y of minus 2 equal to 1 and y prime of minus 2 equal 3. This means that we are going to solve for getting C1 and C2. Okay, so the constant, the C1 and C2 in our equation going to be solved by using this additional conditions for the equation. You can solve this for the home assignment. Another one for the home assignment similar to the previous one, y double prime plus y prime minus y equal to 0. And it is an initial value problem, so you can find C1 and C2. Y of minus 4 equal to 7, y prime of minus 4 equal to 1. You can solve this and find C1 and C2 and find the general solution. Okay. Actually, this is the video for today. I hope that you have understood it well, and I hope that you can get through the constant coefficient case. Try first to solve all the examples in the video, and then solve the in-class assignments by yourself, and then submit the home assignment through the iCampus. Okay, Thank you, and see you in the next video.